Chapter 5, Section 2, Scaling. In this section, we will discuss techniques to adjust numerical data for more effective analysis and machine learning modeling. Specifically, this section will focus on the difference between min-max scaling and standardization. These two techniques are widely used in data preprocessing to ensure that numerical variables are appropriately scaled for comparison and modeling. By the end of this lecture, you will understand what min-max scaling and standardization are, when to use each technique, why scaling is important. Scaling is a data transformation technique used to adjust a range of numerical features to ensure consistency and comparability across different variables. Scaling is necessary when the range of values differs significantly. In many datasets, numerical features have different ranges. For example, in an employee dataset, we might have these features. Employee salaries ranging from $30,000 to $200,000. Performance scores ranging from 1 to 5. Years of experience ranging from 0 to 40. When we use these features for predictive analytics, we often need to apply scaling to these features because the difference in range can cause various problems in machine learning. So, why can differences in scale cause problems in machine learning models? These are main reasons. First, machine learning models are sensitive to scale. Algorithms like k-nearest neighbors and support vector machines compute distances, which can be dominated by large-scale features. Second, gradient-based optimization can be unstable. In neural networks or logistic regression, large values may cause the optimization algorithm to converge slowly or unpredictably. The third is unfair weighting in predictions. Without scaling, a model may give more importance to features with larger numerical ranges. To address these issues, we use scaling techniques like min-max scaling and standardization. Min-max scaling rescales data so that all values fall within a fixed range, typically from 0 to 1 or from -1 to 1. This is the formula of min-max scaling. Here, x is the original value. X-min is the minimum value of the dataset. X-max is the maximum value in the dataset. Let's say we have employee experience levels in years. In this dataset, the maximum value is 40, and the minimum value is 2. So, using the formula of min-max scaling, we can compute the scaled values. Now, all values are between 0 and 1, ensuring fair comparisons across different scales. The following are cases where it is appropriate to use min-max scaling. First, when preserving the original distribution of data is important. Second, when we know the minimum and maximum values. Third, when we use models that do not assume a normal distribution, like KNN or neural networks. However, min-max scaling is sensitive to outliers. If a single value is extremely large or small, it can compress the rest of the data into a narrow range. Let's see an example of a dataset with outliers. The simple example is an employee's salary dataset. In this dataset, the employee A is an outlier, whose salary is extremely high. Using the formula, let's compute the scale values of each case. As we can see, the scale values were compressed into a narrow range. Without handling outliers, min-max scaling can squeeze most of the data into a narrow range, leading to distorted analytical result. Standardization, also called z-score normalization, is another scaling method that transforms data to have a mean of 0 and a standard deviation of 1. We can apply standardization by this formula. Here, x is the original value. Mu is the mean of the dataset. Sigma is the standard deviation. This transformation ensures that the data follows a standard normal distribution, so it has no unit dependency. Let's apply standard deviation to the dataset that records employee experience levels in years. This dataset is the same as the one we used as the first example of min-max scaling. Based on the formula of standardization, first, let's compute the mean and the standard deviation. Standardization is typically performed using the population standard deviation rather than the unbiased standard deviation. Then, using the formula of standardization, we can compute the standardized values. Now, all values are between 0 and 1, ensuring fair comparisons across different scales. The following are cases where it is appropriate to use standardization. First, when data follows a normal distribution. Second, when we use models that assumes normality, such as linear regression, logistic regression, and principal component analysis. Third, when we do not know the minimum and maximum values of the features. Such cases typically occurs when the dataset is incomplete or when new data is continuously being collected. Unlike min-max scaling, standardization is less affected by outliers because it centers data around the mean rather than adjusting to min-max values. This table summarizes the comparison between min-max scaling and standardization. Now, let's implement min-max scaling and standardization by Python. First, import libraries. Import pandas for handling a data frame. And for scaling, import min-max scaler and a standard scaler from sklearn preprocessing. We use this dataset we saw in the previous slides. Using this dataset, we apply min-max scaling and standardization to the column named experience. Let's start with min-max scaling. First, instantiate min-max scaler and store it in min-max sc. Min-max sc is an instance, not just a variable, so its name can be anything. However, it is better to use a name that clearly indicates that it is used for min-max scaling. Then, apply fit transform to the experience column to scale the column between 0 and 1. And store the transformed value in the column named min-max experience. Here, we need to use double squared brackets to enclose the column named experience. It is because fit transform is designed to handle a two-dimensional array, that is, a matrix. So, we need to use double brackets to make a two-dimensional array. Next, apply standardization. We can do it in a similar way. First, instantiate standard scaler and store it in stdsc, an instance. Then, apply fit transform to the experience column to have a mean of 0 and a standard deviation of 1. Then, store the transformed values in the standardized experience column. Let's display the dataset. As we can see, mean max scaled values and standardized values are added as new columns. Let's check the descriptive statistics. As we can see, the variable with mean max scaling has a maximum value of 1 and a minimum value of 0, while the variable with standardization has a mean of 0 and a standard deviation of 1. As the first step of scaling, we created an instance in this way. Some of you may wonder that, what are we doing here? Creating an instance means generating an object from a class. In Python, a class is like a blueprint, and an instance is a specific object created based on that blueprint. Using an analogy, the class mean-max-scaler is a blueprint for building a machine that calculates scaled values. Creating instance by mean-max-scaler with empty brackets, we create the actual scaling machine built from the blueprint. Then, using fit transform method, we send the instruction to operate the machine. The data, here it is the variable named experience, is the material fed into the machine. Then, the transformed data is the final product that comes out of the machine. Let's wrap up. Scaling is a data transformation technique used to adjust a range of numerical features. Scaling is necessary when the range of values differs significantly, because such difference can lower the efficiency and effectiveness of the model. Min-max scaling and standardization are common methods for scaling. Min-max scaling rescales data to a fixed range, but it is sensitive to outliers. Standardization converts data to a mean of 0 and a standard deviation of 1, making it robust against outliers. Choosing the right method depends on the dataset and machine learning model. Thank you for watching. If you have any questions, feel free to ask in the comments. Your feedback is always appreciated.